My name is Mayank Varia, and I research cryptography at Boston University. In this talk, I want to discuss some of the work that my colleagues and I at BU have been doing to make a cryptographic technology called Secure Multi-Party Computation, or MPC for short, more accessible and scalable for data analysts to use. But I want to start by describing why we think this is such an important problem to solve. So I want to tell you the story that begins in 2013 when the former mayor of Boston, Mayor Tom Menino, pledged to make Boston the premier city for working women. To identify ways to close the gender wage gap, he established a women's workforce council comprising industry leaders and businesses large and small across all sectors of Boston's economy, along with social advocates in politics and academia. This council established a pledge, or 100% talent compact. It has since been signed by several hundred companies in the Boston area. Compact signatories pledge to do three things: understand the root cause of the wage gap, use evidence-based methods to close the wage gap, and measure their progress over time. In this talk, I want to focus on that final goal, which I've listed on the bottom left of the slide. So the objective here is to actually measure the gender wage gap from real data, and they were able to get data from approximately 1/6 of the greater Boston workforce. I show on this slide examples of published reports that are available on the City of Boston's websites from their 2016 and 2017 data analyses. This kind of analysis was only possible because we've been able to use cryptography to protect the salary data in transit, at rest, and even while computing using MPC. The workflow for a company that participates in the wage gap analysis is pretty simple. They go to this website, 100talent.org, where they see a few tables that look like the following. This table requests basic demographic information about the number of employees at the company, broken up by gender, race, and job category. This table follows the same format as an Equal Employment Opportunity Commission form that many large employers fill out annually, so they already have this information at this disposal. Subsequent tables on this form look almost the same, except rather than asking for number of employees, they ask for salary information like the total salary and performance-based pay, again broken up by gender, race, and job category. With this information, we can not only measure the overall wage gap, but also better understand its root causes. So this is the information that each organization contributes. So what happens after they click Submit? Unlike most web forms, in this case, when an organization clicks on the Submit button, their salary data doesn't actually go anywhere, at least not in an intelligible fashion. Instead, what happens is that there's local client-side JavaScript that cryptographically splits their data into two pieces, one of which goes to a server that we run at Boston University, and the other piece of which goes to the Boston Women's Workforce Council. These two pieces are individually unintelligible gobbledygook. You can't make any sense of the information received. But the magic of MPC is that collaboratively, Boston University and the City of Boston can work together to calculate statistics or metrics of interest to the city. In this case, just calculating the overall city wage gap. MPC has been used in many other contexts as well, both in the private sector and is increasingly being looked at in the public sector. For instance, on the right side of the slide, I show a paragraph from a pending piece of legislation in the US Congress that, if passed, would use secure multi-party computation to collect metrics about the educational sector. The design of our 100talent.org website is unique in that it uses secure multi-party computation in the first place, and also because it's been strongly motivated by the design considerations for a variety of different stakeholders involved in this data analysis pipeline. I'll describe 4 of them here. First, there are the actual HR personnel who are the ones tasked with uploading their organization's information into this system, into this interface. For them, our primary concern was ease of use. That's a big reason why we're using a web browser interface rather than asking them to install any software or do anything that could be a barrier to using the system. We also ran many different training seminars, both in person and online, to make sure that they were familiar with the system and how it worked. The second stakeholder was the Boston Women's Workforce Council. Their primary concern was the accuracy of the results, given that due to the nature of MPC, they can't look at the data to do any kind of manual post-processing or filtering of erroneous results. For this reason, our website has a lot of client-side JavaScript that runs on the organization's side to identify proactively if it looks like they're making a mistake with data entry. Our third stakeholder are the IT personnel at the organizations that are contributing their data into this analysis. For them, a big concern was to make sure that they understood that the system is actually doing what we claimed it is doing, that it is easy for them to audit and verify that the website is behaving properly. And for that reason, all of our code is open source. Our initial system was a very bare bones system that had just a couple hundred lines of code, although it's since grown a little bit over time to add more features. You're welcome to visit github.com/multiparty to see the code for this project and the others that I'll describe later in this talk. Finally, lawyers at the data contributing companies were worried about risk and the liability if something should go wrong. Some of them asked us to sign non-disclosure agreements stating that we would not hand out their salary information to anybody else. This is a document that we were able to get the BU Office of General Counsel to sign because due to the nature of MPC, we weren't ever receiving their salary information in the first place. So that's our system for making MPC easy to use on the web. In my remaining time, I want to pivot and talk about a different system that we've built to make MPC scalable so that you can do analytics over very large data sets that are held by different private organizations that want to do some collaborative data analysis, but they don't want to share the data with each other. This system is called Conclave, and it works as follows. You can have an analytic that is specified as an ordinary SQL query. So the analyst does not have to know anything special about MPC. And Conclave will split this SQL query into components that are executed using MPC on different providers' existing data parallel frameworks like Hadoop or Spark. You don't have to put your data in a different data engine or platform in order to use it with Conclave. Conclave also includes static analysis tools that will opportunistically identify places to improve performance without compromising on privacy. Specifically, it will rewrite the query in such a way that it tries to front-load as many operators as possible that can be executed locally on each individual backend without the need for MPC so that it minimizes the amount of work that needs to be done globally by all parties. This helps to make MPC scalable to larger data sets. Finally, we include a dispatcher that makes Conclave easier to use either in a peer-to-peer setting between different private organizations or on a multi-provider public cloud. Because Conclave has many moving pieces, like the data parallel stacks that do computation in the clear, and the MPC engines built by us and other people that do the global part to do the global aggregation, there's a lot of different software components. So our dispatcher allows for push-button operation, where once the analytic is specified, it will create containers and execute all the various components of the system on the different backends for you. Finally, one ongoing project of ours is to use FPGAs to have hardware-accelerated MPC in the data center. We think that FPGAs are a great fit for MPC because FPGAs offer the ability to parallelize a lot of computation, and MPC tends to be embarrassingly parallel. And also, FPGAs in the data center offer very fast network connectivity speeds, very high-speed interconnects, which comes in very handy because MPC tends to be communication-bound in practice. Our initial experiments show that we can design an MPC system on an FPGA that allows for both arithmetic and Boolean circuits, and the punchline is you can basically get the equivalent of a 200 megahertz CPU processor. So that's slower than ordinary processors, but you get the equivalent of a 200 megahertz processor with the huge benefit that all of the computation is being done in a cryptographically protected fashion, and none of the individual participants in the system know what the data say. In conclusion, we believe that making MPC more accessible and scalable can fundamentally change the way that we go about data analysis. Rather than having to think first about what data you can acquire and then trying to think about what questions you can ask of that data, you can flip that around and first decide what question you want to answer if you had access to all the world's data, and then figure out how to protect that access sufficiently so that the data owners consent to participate. Thank you for your time.